Now let's start with a new proceeding domain of our lectures, and that is scattering. Actually, in our syllabi, we have to only go through the elastic kind of scattering, and we understand what elastic means when there is conservation of kinetic energy before and after the scattering. So we would like to start here with a formalism known as scattering matrix, and then in the same domain we will try to connect this scattering matrix to unitary transformation, and at the same time we will incorporate the transition matrix as we move on. Now, the first question arises that what is this scattering matrix, and what's its importance? Basically, the scattering matrix, or we also call it as S matrix, and it's basically a central object in the theory of scattering, and that basically connects. We have some initial state and initial quantum state before the scattering, and the final quantum state after the scattering. So if I have a state A and the state B, this S matrix it connects this initial state with the final state. So in between there is interaction, in between there is scattering. So scattering to me is more advanced than that of all the things that we have done in quasi-classical case, where we discussed the problems in which we have discussed thoroughly the transmission of particles, interaction of particles with the potential, and if we rightly go back to the process where E is less than that of V and E is greater than that of V, this E greater than V naught leads to the phenomenon of scattering. So the scattering has its roots in the problems of quasi-classical cases where we have the interaction of the particle with independent potentials. Now, so proceeding from here, what we have is S matrix, and what it does basically, it connects the initial state. The initial state in our case is certainly the state before the scattering, because this is all quantum mechanical. So drawing of trajectories is a nuisance. There's no point in drawing any diagram here. So the point is that this scattering matrix, what it does basically, it connects the initial state with the final state. So the final state is a result that we have after the scattering, and the initial state is a result. It's also a result without having an interaction with an obstacle. And what it does, it essentially encodes. I should quote down here. It encodes the full information about the scattering process, transforming incoming states, the initial state, into the outgoing states. So we can call it also incoming state, and this is my outgoing state. Now, in quantum mechanics, this S matrix that we have, it can be understood as describing the evolution of particles. Right? So that will be a better word: evolution of particles interacting with the potential. interacting with potential. Potential. So, so if I have to translate it down in some other words, uh, like we have the evolution. I'm not talking about biological evolution. There may have a good contact between the quantum mechanical evolution and the biological evolution. But here, what we have is we have something in past and we have something in future. So, so I can say that this S matrix that I'm talking about, it can be we can have an understanding on it by describing the evolution of these particles that are interacting with the potential from the time long before the interaction. Uh, I should call it asymptotic past to a time long after the interaction, and that will be our asymptotic future. So this is our asymptotic past, and this is our asymptotic future. Now, to trace this thing in some mathematical form, if we denote the initial state, that means if I denote the incoming state by psi in, and the outgoing state, so let me write down here outgoing state, so to make it simple, as psi out, O for out, then there is a correlation between this incoming state and the outgoing state. The information is in that correlation that's between this incoming state and the outgoing state, and these two states can be correlated via this scattering matrix. So this scattering matrix, if I represent it by S, then the state out has the relation with state in via this S matrix, via this scattering matrix. And we can generalize this S here as e to the power of h naught t, keeping iota, times e to the power of I h t, which minus e to the power of minus h naught t dash. Now, what is important here is I must quote a limit here. So limit for this t tends to plus infinity, and the t dash that I have introduced here, this t dash tends to minus infinity. Now, let's go with the symbols that are out here. This H is a full Hamiltonian, and this H also includes the interaction potential V. And this H naught, it's a free Hamiltonian. That means something before the actual interaction. So there is no interaction involved in this Hamiltonian. It's only the kinetic energy term that's inculcated here. And then we have the time evolution of the states under these Hamiltonians, and the time evolution of these of the states under these Hamiltonians gives rise to scattering. So drafting down this mathematical format for this scattering matrix is as simple as anything, like having scattering defined as the time evolution of the states. Under these Hamiltonians, this Hamiltonian is dependent on the potential, and these two Hamiltonians are independent of their potential. Now, let's connect this S matrix to a unitarity. Now, I think the key feature of this S matrix is that it is unitarity. I mean, which ensures the conservation of probability in quantum mechanics. So what's that? Unitarity. And this unitarity is a result of, if I have S dagger and S, and this is equal to SS dagger, then this is equal to I. Now this condition reflects that the total probability, so this is my probability, I mean the, the norm of the wave function, the total probability must remain conserved. It must remain constant. It must remain unchanged during the scattering process. Because we are in the domain of elastic scattering, and 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 these probabilities that we have, they must remain unchanged. And no particles are created or destroyed. So the point is, no particles are created or destroyed. Only then we can have this condition of conservation of total probability. Total probability conservation. So, and you have the incoming particles and you have the outgoing particles. That means the number of particles that are interacting and the number of particles that are coming and interacting, and the number of particles that are interacting and coming out of interaction, their number is constant, and there is no destruction or creation of any particle. Now, this S matrix, we can write it in terms of the transition matrix. Transition matrix. So we have scattering matrix and we have transition matrix. And this correlation between scattering matrix and transition matrix can be written as, okay, so I can write down this S matrix as I plus 2I T. Now what does it mean? Where this I that I wrote down in the previous case as well, this I is our identity matrix. Identity matrix. And this matrix corresponds to no scattering. That the particles continues along its initial path. That's what this I means. And T that I have written down here, this T describes the scattering effects. Scattering effects due to potential. Now, this T matrix is used in some perturbative expansion of scattering amplitudes, which we will discuss when we talk about, which we may discuss when we go into the details of Born approximation. But here, we are trying to execute a formalism for this scattering. Now, we have unitary transformations. In quantum mechanics, we have unitary transformations, and we use them. And these unitary transformations, what they do basically, uh, they describe how quantum states evolve without changing the total probability. So there is a clean connection between this unitary transformation and the scattering processes that we have been talking about here, because we have to ensure that the probability is conserved in a scattering process, in this elastic scattering process. Now these transformations are associated with time evolution of the system, and these transformations are implemented by unitary operators. And what are these operators? They are u of t. And and using these unitary operators, we can evolve the state from one time to another time. That should be the case. So if I write down my process, my phenomenon, I have a state at t, and I use this unitary transformation, and I have a state, say some 0, where this u of t is a unitary operator, and this operator should satisfy the condition that its dagger and itself is equal to the identity matrix. Now, this S matrix itself can be seen as a unitary transformation that evolves the system from some remote, I should call it remote past, to some remote future. So they must have same kind of objectivity linked with S matrix as that of the unitary as that of this unitary transformation. So the S matrix, if I have to write down this in some mathematical sense, it has to be this unitary transformation, which moves from some plus infinity to some minus infinity. Now this operator transforms the asymptotic in state, that means a state long before, to an asymptotic out state, a state long after. Long before, long after. Now again, I think it's again important to go back to the idea of incoming state and the outgoing state. Now, if I go with incoming state, what's that? That is my state psi in. And what does this incoming state tells me? It tells me, in the domain of quantum mechanics, it tells me that the state in some distinct past before interaction with the scattering potential. This is also referred to as a free state. You should also call it as a free state. That means no influence from the potential. And then we have the outgoing state. And that is psi out. And this is the state after the particle has interacted. It has interacted with the scattering potential. And has reached to some distant future. This is how it has to be. It has to be sensed, at least. And we have this S matrix. We have this psi out, as I wrote down before, to have a relation with psi in via this scattering matrix. Now, if we move from here, what we have is we have to go with the mathematical structure of this S matrix, and we have to code down that, and we may have to use some more plausible symbols to describe the mathematical structure. And if I take on from here, and I have a matrix, I have an S matrix, and I write it as SK dash and K. And it represents basically the transition amplitude from the initial state to the final state with the change in momentum, because if there is some transition, then you can link up the transition in terms of the momentum. So momentum is linked with the K, so I can say that I have the initial state momentum, initial state momentum K, and final state momentum as K dash. So mathematically, if I take the dagger of SK dash K matrix and multiply with it with SK dash K, this is going to give me an identity matrix. So what does that mean? That means mathematically this S matrix, so if I take S dagger and S, from here I should get an identity matrix. So this S matrix is unitary, meaning it itself, the condition S dagger S is equal to identity matrix, a unitary matrix. What is this S dagger? S dagger is the Hermitian conjugate, and we understand that it is Hermitian conjugate, or we may also call it as adjoint of S matrix. And what is I? I is the identity matrix. Ensuring, and this I is actually ensuring, it's ensuring the probability conservation. Ensuring probability conservation. And as I wrote down previously, this S matrix as I plus 2IT. This equation shows that S matrix can be decomposed. It can be decomposed into two parts. The first part is the identity part, and this identity part corresponds to no interaction. So I should write down this. So I, that's in that equation, it corresponds to no interaction. And that means free propagation. Free propagation. And then the next term is T part. And what's T? It encodes basically. This T encodes the scattering dynamics. The scattering dynamics due to the potential. Now, let us move on from here and consider the basis. If I consider the basis of momentum eigenstate. Eigenstate, what's that? say that's ket of K. The matrix element S matrix. So S, K dash and K will be what? That will be the expectation of K dash, then S and K. Now this Sk dash K gives us what? It gives us the probability amplitude. It gives us probability amplitude. And probability amplitude that a particle with initial momentum K is scattered to a state with final momentum K dash. So initial state K to a state with final momentum K dash. Now in the case of elastic scattering, the momentum magnitude is conserved. So only the direction changes here because the momentum is conserved, because we are talking about the conserved elastic collision. Momentum is conserved. If momentum is conserved, then what's changing? Only direction is changing. Now, if we have to write down this S matrix, we can write this S matrix as an infinite dimensional matrix where each element represents a transition. See the beauty here. You can boil down it to a long range of states, but each element is representing a transition between two momentum states. So if I try to write down this kind of matrix, what it will look like is S. Here I'll have K1 and K2. Then the next S, I'll have K. This is the first row and second column, K2. Then S, K1, K3, and so on and so forth from this direction. From here we will have S, K, 2, K1. Then we'll have S, K, 3, K1. So here I'll have S, K, 2, K2, and so on and so forth, and so on and so forth, and so on and so forth, and so on and so forth. This is my S matrix, where this S, Ki, so I can write it as Ski, Kj. What it does, it presents the probability amplitude. Probability amplitude for a particle to have a transition from Kjth to Kith state. Right. Now let's extend the same kind of evolution with T matrix. And T matrix is what? It's a transition matrix where I wrote down that equation for S matrix and T matrix. So for T matrix, which is also called as transition matrix, what it does, it provides a more direct connection to the potential, more direct connection to potential V that causes scattering. Now, what it does basically, it represents the part of scattering process due to the interaction with the potential. And we have the relationship between S matrix and T matrix. What's that? That is S is I plus 2IT. I'm writing this equation third time. So we can say here that this T matrix describes the deviation from the free particle, because this I is giving us the measure of free particle. So the T matrix here, it gives us the diversion from the free particle behavior that's caused by the scattering potential. And the matrix element of this T matrix can be defined. This t, k dash and k will be k dash t and k. Now these elements, they give the probability amplitude for the particle with initial momentum k to transition to the final momentum k dash due to the interaction. So interaction is here. So you're moving from k to k dash. And the matrix form of this T matrix can be represented as an infinite array, as we did in case of the scattering matrix. And better is to mark down that. So T matrix, so what is it? It is T K1 K1. Maybe I committed a mistake in case of maybe was that a mistake? No, yeah, it was a mistake. So here it is SK1 K1. So then it is K1 K2. So this is the part of the mistake that I have committed, and okay. So then I have T K1 K2, and then I have T K1 K3, and so on and so forth. So here we have T K1, sorry, K2 K1, then T K2 T K2, and so on and so forth. And here we will have so on and so forth, and here we will have so on and so forth, and here we will have so on and so forth. Then this is an infinite array of the matrix. So each element that we have here is basically T, Ki, Kj. And what they do, they represent the scattering amplitude for a particle making a transition from Now this transition involves potential from Kj to Ki due to the scattering potential that I was trying to tell you. Now, if we go back to perturbation theory, the T matrix can be expressed in terms of interaction potential and as a series of expansions, and the first Born approximation gives the lowest order term for this T matrix, and I would like to write down that as TKK1, and that is our matrix element of K dash V and K. Now, in higher order approximations, the T matrix includes multiple scattering events. So the full T matrix is related to potential V through the equation known as Lippmann-Schwinger equation. So I would like to at least write down Lippmann-Schwinger equation. So what's that? That is T is V plus Vg naught T. And V is our scattering potential. And this G naught is it's a free particle Green's function. Free particle Green's function. We may use it. That describes the propagation of the particle in absence of any kind of potential. And this equation can be solved iteratively to obtain the exact T matrix, and which can include contributions from all scattering processes. So with this, I would like to stop here. At least I tried out to present some basic idea of T matrix and S matrix. S matrix is our scattering matrix, and T is our transition matrix. Now, if I conclude my talk, what we have tried, we have talked about S matrix, and this S matrix does, it describes the transition from the incoming state to the outgoing state in a scattering process. Then I talked about unitary transformation, and it is unitary in a sense that if we take the dagger of S and multiply with S, it gives us an identity matrix, and can be written as, and we can have a relation like S equal to I plus 2IT. Now, in matrix form, each element that we have, what was that? It was S, K dash, and K represents the scattering amplitude from the initial state. The initial state is K to the final state, K dash. And in terms of T matrix, what we tried, so to summarize the T matrix, what it does basically, it encodes the effects of interaction of potential during scattering. So you have an interaction with the potential, and it relates S matrix as S is I plus 2IT. And what else it does? In matrix form, each element of this Tk dash K, they represent transition amplitudes. Transition amplitudes due to potential. So due to potential, it's more important here, from the state K to the state K dash. So both these matrices provide different perspectives on the same scattering process. The S matrix, what it does, it describes the full evolution from initial state to the final state, whereas T matrix focuses on interaction that's responsible for that kind of transition that's taking place. So with this, goodbye and have a nice time.